All right, you crazy fuckers, you ready to get your minds blown?
Oh, yeah. Always ready to dive into some seriously mind-bending shit.
This time we're talking quantum algorithms. I've got expert speaker here to break it all down.
So strap yourselves in, folks, because we're about to go deep into the world of quantum mechanics. Forget Netflix recommendations. We're talking about algorithms that can crack the encryption we use today. Stuff that makes your head spin.
Yeah, no more messing around with those basic algorithms. We're going full quantum, baby.
Exactly. We're talking about harnessing the power of qubit.
Qubits.
Yeah, think of it like this. A regular bit is either a 0 or a 1.
Right.
But a qubit, it's like a goddamn superhero. It can be in both states at the same time.
Whoa, okay. You're blowing my mind already.
Yeah.
But how the hell do we actually use these qubit superheroes?
That's where quantum algorithms come in.
Okay, I'm reading this paper by this Andrew Childs guy. He mentioned something called universal gate sets.
Ah, yes.
Yeah.
Universal gate sets.
It sounds kind of kinky.
Not quite. But they are the building blocks of quantum algorithms. Think of them like Lego bricks. Each gate performs a specific operation on our qubits. You can flip them, rotate them, even entangle them.
Entangle. Like quantum love.
Ha ha! Something like that. It's basically quantum telepathy. But we can get into that later. For now, just know that these gate sets are what make quantum algorithms so damn powerful. Childs even says that classical algorithms are just inadequate for tackling certain problems.
Inadequate. Is that like calling them slow and fat to their digital faces?
Pretty much. We're talking about problems that would take classical computers, even the superpowered ones, billions of years to solve.
Okay, so what kind of problems are we talking about here? Give me the juicy stuff.
Well, for one, factoring insanely large numbers, which is the backbone of modern encryption.
Wait, hold up. Are you telling me these quantum algorithms could crack any code? Someone needs to tell the goddamn CIA.
Well, it's not that simple. But they do have the potential to break the encryption we use today, especially with something called the discrete log problem, which Childs mentions.
Discrete log problem.
Yeah, it's kind of complicated, but just know that it's the foundation of a lot of our online security.
Okay. So maybe we should keep this quantum stuff under wraps. This other paper, I'm looking at this black box quantum walk thing. They're talking about mapping out the unknown. It's like some Indiana Jones shit. What are these quantum walks?
Imagine a classical algorithm is like a rat in a maze, right? It can only go down one path at a time.
Right.
A quantum walk is like a goddamn ninja. It can explore all paths simultaneously.
A ninja rat.
Yeah, something like that. They use this technique to solve problems related to searching and optimization. Things like finding the best route for a delivery truck or optimizing financial portfolios.
Yeah, that's efficient. But this paper also mentions something about simulating Hamiltonians. What the hell is a Hamiltonian? Sounds like some kind of exotic liquor.
It's actually a lot less fun than it sounds. A Hamiltonian is a mathematical description of a quantum system.
Okay.
And simulating one, it's like trying to predict every single move in a game of chess.
Chess. How many goddamn moves are we talking about?
1 billion. On a board the size of the universe.
My brain hurts.
Tell me about it.
So why bother? Why even try to simulate these Hamiltonians?
Because it allows us to study complex quantum systems. Things like how electrons behave in materials, or how molecules interact with each other.
So we can create new materials with quantum precision, like some futuristic Iron Man suit.
Exactly. And this interaction picture paper dives into a technique that makes these simulations even more efficient.
Efficient is good, especially when you're dealing with all this quantum craziness.
Absolutely.
But let's back up a bit. This Lin paper, seems like they're laying down the law here, the fundamental principles of this whole quantum shebang.
Think of Lin's paper as the quantum rulebook. It breaks down the core concepts like superposition and entanglement.
Superposition, that's the whole being in multiple states at once thing. Right?
Bingo!
Oh.
It's like a quantum coin flip that lands on heads, tails, and D its side, all at the same time.
My brain is melting. And entanglement? That sounds messy.
Basically, it means that quantum particles are linked, even if they're miles apart. You change one and the other one changes instantly.
No way. Spooky action at a distance.
Yeah.
So it's like quantum particles are having a Zoom call across the universe.
Pretty much. And these concepts are crucial for understanding how quantum algorithms actually work.
Right. Because knowing how to drive a Tesla doesn't mean you understand how the damn thing works.
Exactly. Lin gives us a peek under the hood of this quantum machine.
This is some heavy shit.
Yeah.
We've gone from quantum gates to quantum telepathy, and now we're diving into the fabric of reality itself. I need a goddamn drink.
We'll get to that. But first, we got to talk about how we can actually USE this quantum madness. And trust me, things are about to get even wilder. All right, so we're back and ready to dive deeper into this quantum madness. You ready?
Hell yeah. Hit me with your best shot, expert speaker.
Okay, well, last time we were talking about the fundamental laws of quantum mechanics. Remember those?
Vaguely. My brain's still a little fried from those quantum cocktails.
Fair enough. Well, this time, let's see how we can actually USC this crazy shit.
Okay,
Yeah.
now you're talking. Less theory, more action. Let's do this.
Okay, so I'm looking at this paper. It's called Low Optimal Spectral Norm.
Low optimal spectral norm. Sounds like a rating for a bad sci-fi movie.
It's actually all about efficiency. You know how we talked about simulating Hamiltonians before the break?
Yeah, those mathematical beasts that describe quantum systems.
Right, well, this paper is all about optimizing algorithms to exploit something called sparsity.
Sparsity. Sounds kind of kinky. Like a quantum orgy where only half the particles show up.
Not exactly, though I appreciate the imagery.
So lay it on me. What is the sparsity thing?
Think of it like this. A sparse Hamiltonian means that most of the interactions in that system are negligible. It's like a giant social network where most people only talk to a handful of close friends.
Got it. So instead of analyzing every single goddamn interaction, you can focus on the ones that actually matter. Less noise, more signal.
Precisely, and this paper is all about optimizing algorithms to exploit that sparsity. We're talking about speeding up those simulations by orders of magnitude.
So even in the quantum world, time is money.
Got it.
But this paper also throws around terms like block encoding and quibitization. Am I even speaking English anymore?
It's all part of the quantum lexicon. Don't worry about the jargon. The key takeaway here is that we're finding clever ways to represent classical data in a quantum form. It's like translating Shakespeare into emojis. You're still telling the same story, but you're encoding it differently.
So our quantum computer can actually understand it. Got it. But something in this paper kind of freaks me out. Even with all this quantum power, sometimes the best we can do is get close enough. What's that about? You're telling me this quantum shit isn't perfect.
I hate to break it to you, but quantum computers aren't some magical solution to every problem. They still have their limitations.
Ah, come on.
But the exciting part is that even with approximations, we can achieve a very high degree of accuracy.
So we're saying, look, we may not have cured cancer, but we made a damn good pizza.
Yeah.
Close enough, right?
You got it. Sometimes a good approximation is more than enough to make groundbreaking discoveries.
I can get behind that. Speaking of groundbreaking, this Ronald Wolfe paper keeps popping up. It mentions teleportation. Are we talking Star Trek shit here?
Not quite. But quantum teleportation is a very real thing. It's the ability to transfer the state of one qubit to another, even if they're miles apart. It's like sending a telepathic message without any physical transmission.
Okay, now you're just messing with me. How is that even possible? Is this black magic?
It's all thanks to entanglement, that spooky connection between quantum particles. Remember how we talked about them being linked even across vast distances? Well, entanglement allows them to share information instantaneously.
So basically they have a secret communication channel that breaks all the rules of physics. That's insane.
Pretty much.
But how is this quantum teleportation useful?
Yeah.
Can I teleport my beer to my hand without getting off the couch?
Not yet. But it's not completely outside the realm of possibility.
Okay.
For now, quantum teleportation is mainly used for quantum communication and networking. But it has the potential to lead to some seriously disruptive technologies.
Like what? Give me some examples.
Unhackable communication channels. Insanely fast data transfer. The possibilities are endless.
Okay, now that's some seriously next level shit. But let's get back to breaking codes for a second. This Wolfe paper also mentions Simon's algorithm, another code-cracking machine.
You could say that. Simon's algorithm was one of the first to demonstrate the power of quantum computation. It can find hidden patterns in data exponentially faster than any classical algorithm.
So it's like having a quantum detective who can sniff out clues in seconds that would take a normal detective years to uncover.
Precisely. And this is a huge deal because it proved that quantum computers could actually outperform classical ones.
In certain tasks, at least.
Exactly. But it paved the way for even more powerful algorithms, like Shor's algorithm, which can crack the encryption we use today.
So we're all going to get hacked by these quantum algorithms?
It's a possibility. But hopefully we'll have better security measures in place by then.
Hopefully. But enough about breaking the internet. This paper, Skate Preparation and Arithmetic, sounds kind of boring. Are we balancing checkbooks now?
Not quite, but it is a fundamental challenge in quantum computing. Think of it like setting up a line of dominoes.
Okay.
If you don't set them up just right, the whole thing falls apart, right? Well, state preparation is about making sure that our qubits are in the right state so that our quantum algorithms can run properly.
So it's all about getting those quantum ducks in a row.
Exactly. This paper explores different techniques for preparing these states efficiently and accurately, which is crucial for building reliable quantum algorithms.
Makes sense. Garbage in, garbage out, even in the quantum world. Now, this next one is a mouthful. Uniform spectral amplification. Sounds like some kind of audio equipment.
Not quite, but it is about amplifying something. Imagine you're trying to listen to a faint radio signal. This paper is about amplifying that signal so you can actually hear it.
So turning up the volume on the good stuff and drowning out the noise. Got it.
Exactly. And in the quantum world, this signal is the outcome that we want from our quantum algorithm.
Okay. So we've got our quantum dominoes lined up. We've amplified the signal. But I'm still a little fuzzy on the bigger picture here.
Well, I got just the thing for you.
Hit me.
This Nielsen and Chuang paper, this is like the quantum Bible. It lays down the theoretical foundation for everything we've been talking about, from the basics of qubits and entanglement to the design of complex quantum algorithms.
So if I read this, I'll be a quantum expert.
Maybe not an expert, but
Yeah.
you'll definitely have a much deeper understanding of how this stuff works.
Consider me intrigued.
Good. Now let's move on to this survey of applications and end-to-end complexities paper. It sounds a bit dry, but trust me, this one is full of exciting stuff.
All right, what do we got?
This paper gives a really good overview of how quantum algorithms can be used to solve real-world problems. And we're not just talking about theoretical stuff here. We're talking about practical applications in fields like medicine materials, science, finance, you name it.
Hold on. I thumped the brakes a little bit. That's a lot to unpack. Okay, so let's talk about these real-world applications. This survey paper mentions something called condensed matter physics. What the hell is that? It sounds kind of dirty.
It's not as exciting as it sounds. Basically, it's the physics of solids.
Solids, like rocks.
Not just rocks. We're talking about materials with really interesting properties, stuff that conducts electricity with zero resistance. Or bends light in weird ways.
Okay, now that's pretty cool. But how do these quantum algorithms help us actually design these materials?
Remember those Hamiltonians we talked about? The
Yeah.
mathematical blueprints of quantum systems?
Yeah, vaguely.
Well, these algorithms can simulate those blueprints for super complex materials, which lets scientists figure out their properties before they even try to make them in a lab.
So we're talking about a crystal ball for material science. No more mixing random shit together and hoping for the best.
Exactly. And this paper specifically talks about the Fermi-Hubbard model. It's basically a way to describe how electrons interact in solids.
Sounds complicated.
It is. Simulating it accurately on a classical computer, next to impossible. But quantum algorithms might be able to crack it. And that could lead to breakthroughs in all sorts of fields. Superconductivity, solar energy, you name it.
Damn. So quantum algorithms aren't just some abstract theoretical thing. They can actually have a real impact on the world.
Absolutely.
What other industries are going to get a quantum makeover?
Well, the pharmaceutical industry is a big one. Imagine designing drugs with atomic precision.
Hold up. Are you talking about curing cancer with quantum computers?
Yeah.
That's some seriously futuristic shit.
It's definitely a possibility, though we're not quite there yet. But quantum algorithms can definitely speed up the drug discovery process. This paper mentions something called the vibrational structure problem. It's basically about understanding how molecules vibrate at the quantum level,
Why do we care if a molecule is in the mood to shake it?
because those vibrations affect how molecules react with each other and how they interact with light, which is super important when you're trying to design new drugs.
So we're basically trying to choreograph the molecular dance floor to make better drugs.
Something like that.
Okay, I'm down with that. But this paper also mentions something called quantum field theory. Isn't that some really high-level physics stuff?
It's the big leagues. Quantum field theory tries to explain, like, the fundamental forces of nature, the very fabric of reality.
Okay, now we're getting deep. How the hell do quantum algorithms help us understand the universe?
Simulating quantum field theory on a classical computer. Pretty much impossible. But quantum algorithms might be able to handle it. We could study the early universe, black holes, dark matter, all that crazy shit.
You've officially blown my mind.
Yeah.
Let's bring it back down to earth for a second. This optimization stuff. This
Mhm.
paper talks about financial modeling, machine learning, all sorts of crazy shit. So these quantum algorithms can make us rich and predict the future.
Maybe not that, but they can definitely help us make better decisions. Optimization problems are everywhere. Finding the best route for a delivery truck, optimizing your stock portfolio, training a machine learning algorithm to predict customer behavior.
So basically, if you're trying to find the absolute best solution out of a million possibilities, a quantum algorithm can help you do that way faster than a classical algorithm.
Exactly. This paper talks about quantum linear system solvers, which could revolutionize a ton of different fields: finance, logistics, even artificial intelligence.
Well, my brain is officially fried. We've gone from zero to quantum hero in like an hour. Any final thoughts, expert speaker?
I think the biggest takeaway here is that quantum algorithms aren't just some theoretical pipe dream. This stuff is going to change the world.
No doubt about it. Well, that was one hell of a deep dive. We've covered everything from quantum teleportation to the Fermi-Hubbard model. Big thanks to expert speaker for joining us and breaking it all down.
Anytime. Happy to geek out with you any day.
And to all you listeners out there, thanks for tuning in. We'll catch you on the next deep dive.